Welcome to the Explainer. Today we're doing something a little different. We are going to treat polynomial math like a thrilling detective case. Our mission, tracking down all the missing zeros of a polynomial function. Now, I know that might sound a little daunting, but stick with me. By the end of this, you'll be solving these like a seasoned investigator. So let's start with the big mystery here. How exactly do you find the invisible zeros of a complex polynomial, especially when some of them don't even show up on a standard graph? It's a puzzle, right? It requires us to look beyond what's just sitting right in front of us. And today, we're going to build the exact toolkit you need to crack it wide open. Here's our roadmap for the investigation. We'll start by demystifying polynomial zeros, then cover the fundamental theorem, look at how complex zeros travel in pairs, round up our suspects, run our interrogations using synthetic division, and finally, put it all together into the ultimate solution strategy. All right, phase 1, demystifying polynomial zeros. What exactly are we hunting? The core definition of our target is actually surprisingly simple. A zero of a polynomial is just any value, let's call it c, that makes our function equal absolute zero. You plug it in as your x value, and poof, the whole equation just vanishes into thin air. That's the culprit we're looking for. Now, there's a really fundamental difference between our suspects. Real zeros, they leave clear footprints. They're your visible x-intercepts on a graph. You can literally point right at them. But then we have the tricky ones, non-real complex zeros. These guys are entirely invisible on a standard XY graph because, well, they aren't real x values. You absolutely cannot see them just by looking at a picture of the function. And that is exactly why we need our deductive tools. Moving right along to phase 2, the fundamental theorem, or as I like to call it, the rules of the game. The most crucial clue we have is this exact number right here, n. In any polynomial, n represents the highest degree, or power, of the equation. And according to the fundamental theorem of algebra, that exact degree n tells us the precise number of complex zeros that exist for that polynomial, as long as we make sure to count any repeated zeros according to their multiplicity, of course. It's the ultimate clue, really, because it tells us exactly how many answers we're looking for. Let's look at an actual case file. If we have a degree 5 polynomial, it can have at most 5 real zeros. It might actually have fewer than 5 distinct ones if some of them repeat. And it could be a mix of real zeros and those invisible, non-real complex zeros we talked about. But the unbreakable rule, it must have exactly 5 complex zeros in total when we count that multiplicity. That's our hard limit. We know we need to catch exactly 5 culprits, no more, no less. Phase 3, complex zeros in pairs, the accomplices. There is an amazing built-in shortcut here called the conjugate pairs theorem. If our polynomial has real coefficients, non-real complex zeros will literally always occur in pairs. So if you manage to find one non-real complex zero, say 3 plus 2i, its complex conjugate, 3 minus 2i, is automatically an accomplice. You get a 2-for-1 deal. This also means that the total number of non-real complex zeros in these specific polynomials must always be an even number. Think of this next part like a translation matrix. When we find a zero, whether it's real or complex, we can instantly translate it into a linear factor of the polynomial. If a zero is 3, the factor is x minus 3. If a zero is 2 plus I, the factor is x minus that entire quantity of 2 plus I. Notice how identifying a zero immediately gives us a vital piece of the polynomial's genetic makeup? It gets us one step closer to solving the whole puzzle. Okay, phase 4. Rounding up the suspects using Descartes and rational zeros. Let's dive into our first profiling tool, Descartes' rule of signs. This is a brilliant little trick that lets us predict the possible number of real zeros before doing any heavy math. All you do is look at the polynomial and count how many times the plus and minus signs change between consecutive terms. Just counting those sign variations gives us major clues about how many positive real suspects we're actually looking for. So how do we actually interpret those sign changes? Well, if you have 4 sign variations, you might have 4 positive real zeros, but you might also have 2 or even 0. Notice how the actual number of real zeros can be less than the sign variations, but it always steps down by an even integer. It's a super fast, powerful way to narrow down our profile before we even start the interrogations. Next, we need specific names for our suspect list, right? For that, we use the rational zeros test. This systematically generates a list of potential candidates. We take all the factors of the constant term at the very end of our equation, we call those P, and we divide them by all the factors of the leading coefficient at the very front, which we call Q. By forming all the combinations of plus or minus P over Q, we get a complete list of every possible rational zero. They might not all be guilty, but I guarantee you the guilty ones are absolutely on this list.
Phase 5. Interrogation by synthetic division. This is where we finally find the guilty parties.
When you're using synthetic division to test a candidate, you just need to remember this golden rule. When a remainder of 0 is obtained, the candidate is a 0. A remainder of 0 means the suspect fits perfectly into the equation. It leaves absolutely nothing behind. If you get a 0 remainder, congratulations, you have caught a guaranteed 0. Let's see how this builds in practice. Imagine we're solving a cubic equation. First, we use the rational zeros test to identify our candidates. Next, and here's a pro tip for you, always test the small integers first. Think plus or minus 1, 2, or 3. Use synthetic division on those early on. It saves so much time. Once we hit that perfect 0 remainder, we use the factor theorem to rewrite the equation and essentially reduce the polynomial's degree. By chipping away at the degree like that, we isolate the remaining culprits until the whole case is closed. Finally, phase 6, the ultimate solution strategy, closing the case. This is the master strategy. It's literally the only checklist you'll ever need to close a case, so follow this exact flow every single time. 1. Look at the degree to find your total possible zeros. 2. Use the rational zeros test and Descartes' rule to build your list of candidates. 3. Interrogate those candidates with synthetic division. 4. As soon as you find a 0, apply the factor theorem to reduce the polynomial. And 5. Once you reduce it all the way down to a quadratic equation, you just solve those remaining pieces using standard factoring or the quadratic formula. Stick to this method and trust me, no 0 can hide from you. By systematically uncovering these invisible numbers, you've learned to solve mathematical mysteries that most people just run away from. You've taken complex, abstract concepts and broken them down using logic, structure, and targeted investigation. Which really makes me wonder, if you can master these hidden mathematical clues to track down the invisible, what other complex mysteries are you going to solve next? Think about it.